prove that the sequence 1 times 3 times 5 times dot, 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 and so on, all the way up to 2n minus 1 over 2 to the n times n factorial is convergent. So that general term is quite complicated. If you just look at the top, so you've got this so that general term is quite complicated. If you just look at the top, well, you've got this 1 times 3 times 5 and so on. Well, that is the odd numbers. So your 2n minus 1 is the nth term of the sequence of the odd numbers, just whatever n is, you times it by 2 and you minus 1 and you will get then that odd number. And on the bottom, we've just got 2 to the n, so whatever n is, raised 2 to the power of that times n factorial, right? So basically, I can see from this, you're always going to be multiplying by something to get from one term to the next. If you just look at the numerator, you're always going to multiply by the next odd number. If you look at the denominator, well, the 2 to the n just means you times by another 2 each time. And the n factorial, well, you just multiply by n each time. Think about n factorial is n times n minus 1 times n minus 2 and so on. So then if I take my n factorial and then times it by n plus 1, then that gives me n plus 1 factorial and so on. So for all three of these bits that make it up, so as in the odd number part and the 2 to the n part and the n factorial part, you're multiplying by something to get from one term to the next. So what that means is that this is a geometric sequence. So if you have a geometric sequence, then it means that we can look at it in terms of a ratio. So what you don't want to do is go off and try and differentiate this, or try and say, well, what's the next term? Subtract the current term. That is not going to help you show that this is convergent. The way to do this is to recognize that we've got something that's geometric. And then if we can get an expression for un plus 1 over un, that is the common ratio. You think any geometric sequence, the next term divided by the current term does give you the common ratio. So we can get an expression for that. It should tell us a bit about what is going on with the sequence. So to show that something is convergent, well, if we can show that it is bounded, then we're showing that it's convergent, right? So when you're thinking about showing things are bounded, well, it really, really helps if they are monotonic. So if this sequence is monotone increasing or monotone decreasing, then we can start to get, especially decreasing in this case, then we can start to think about bounds for that. Okay, so if I just think about U1, so U1 as well is going to be, well, it's going to be 1 over 2 to the 1 times 1 factorial, 2 to the 1 times 1 factorial, which is 1 over 2 times 1, which is a half. So the first term is positive. So if we can show that this expression here is firstly positive and secondly less than 1, that would show that the sequence is monotone decreasing, and then we should be able to put some bounds on it. So that is the plan. So, but to get an expression for that, we are going to have to do a bit of manipulation. So if think about un plus 1, well, that is going to be 1 times 3 times 5 times dot, 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 times, well, 2n minus 1. At the moment, this only goes up to n, and then we're going to need the next term as well, which is going to be, it's always 2 more, so it's going to be 2n minus 1 plus 2, which is 2n plus 1. On the bottom, we're going to have 2 to the n plus 1 times n plus 1 factorial times n plus 1 factorial. So that is un plus 1. And if we're dividing that by un, well, we're dividing by 1 times 3 times 5 times dot, 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 times 2n minus 1 over 2 to the n times n factorial. Right, so two things. Firstly, if you're dividing by a fraction, then you can multiply by its reciprocal, so we can flip the second fraction. And secondly, they are incredibly common rearrangements. This 2 to the n plus 1 will be written as 2 times 2 to the n, and the n plus 1 factorial is the same as n plus 1 times n factorial, and that's going to help us a lot, actually. So now we have 1 times 3 times 5 times ... all the way up to times 2n minus 1 times 2n plus 1 over, remember 2 to the n plus 1 is 2 times 2 to the n, and then we have n plus 1 factorial is the same as n plus 1 times n factorial. And we're dividing, so we're multiplying by its reciprocal, so that would be 2 to the n times n factorial over 1 times 3 times 5 times ... all the way up to 2n minus 1. Okay, so now this is going to simplify brilliantly. So the 1 times 3 times 5 times ... all the way up to 2n minus 1. We can cancel this with this. So that has gotten rid of a lot of it. Remember, there'd just be 1, 1, but I'm not going to write that. The 2 to the n can cancel with that 2 to the n. The n factorial can cancel with the n factorial. So we are left with a much simpler expression, which is, so remember what this is as well. So it's un plus 1 over un equals, well, on top, all we are left with is the 2n plus 1 over, on the bottom, you've got 2 times n plus 1, which is the same as 2n plus 2. 2n plus 2. Now, if we look at this, now, so remember, we need to think about what type of number that is. So for all positive integer n, which is what we're interested in, this is a sequence, that's the natural domain of a sequence. 2n plus 1 is going to be positive, 2n plus 1 is definitely going to be positive, and it's also definitely going to be less than 2n plus 2. So that means that un plus 1 over un is less than 1, and it's greater than 0 for all positive integer n. So what does that tell us about the function? Well, as u1, we recall u1 was 1/2 and it was positive to go up. u1, as we recall, was 1/2 and it's positive. As u1 equals 1/2, so un, our sequence, is monotone or monotonic, and it is decreasing as this common ratio is smaller than 1. So each term is getting smaller, and it's every term is positive, right? So because we know it's monotone decreasing, then u1 must be the maximum value. So upper bound equals u1 equals 1/2. And then, well, for a lower bound, and we don't actually have to calculate. Remember, all we are trying to do is show that this sequence is convergent. If we can show that it's bounded, as in we can pick a value that we know it definitely doesn't go below in this case, because we already know the upper bound and we know it's decreasing, then that is enough to show that it's bounded, which is enough to show that it's convergent. So un, we know, is positive for all positive integer n. Okay, remember we know that because the first term is positive and the expression for un plus 1 over un is also positive. So because it's greater than 0, we can take 0 as our lower bound that we know it doesn't go below. So therefore, un must be, well, the maximum value is a half, and we know that it's never goes to 0 because we know it's positive. Now, we don't know how close, but it doesn't matter because the question doesn't require us to know that. So this is enough to show that un is bounded, and so un is a convergent sequence.